Welcome everyone to the Programming Bits and Atoms with Julia by Viral. We are glad Viral can join us today. Without further delay, over to you, Viral.
All right, I'm just going to set up the screen share. All right, so awesome, great to be here. Yeah, Viral Shah, one of the creators of the Julia language and co-founder and CEO of Julia Hub. And I'm going to talk about a slightly different topic than you might have heard me speak about at earlier functional conferences. I'm going to talk about, not just, the Julia programming language, but how we've been using Julia to build programming solutions for the real world, for the physical world. And hence my topic, programming bits and atoms with Julia. A lot of the technologies that we are at Julia Hub today focused on are around modeling and simulation, but we build all of this on the base of the Julia language itself. So for those of you who might not be familiar with Julia, Julia is a functional, not purely functional, but I would say like a practical functional programming language. And the real value for Julia to exist, why should, every time you see a new programming language, you almost always wonder, why do I need another language? Why does this thing exist? And our motivation for starting Julia was to build a programming language that was, solving the two language problem, which was basically, a language that was as easy as Python or MATLAB, high level dynamic languages, but as fast as C. And, um, you know, whether it's on an HPC system or an embedded system, right? At the end of the day, the idea was that we would, solve this two language problem. And, the code, one of our other goals was that the code should be simple. It should look like math. It should allow for people to use high levels of abstraction. And, our focus was on the sort of, the technical computing area. So GPUs were absolutely essential and important to us from the very early days. Automatic differentiation technologies, which of course are at the heart of all the modern machine learning and Gen AI work, but also at the heart of all the scientific computing work that has happened over the last several decades. Um, so this is this is one of our sort of slides from the website, and you can see sort of at the benchmarks that Julia kind of, this benchmark is comparing the speed of all these different languages to C, and on these very small set of micro benchmarks, you can see that Julia matches C. Of course, since we used to talk about these benchmarks, now it has been almost 7 or 8 years, and Julia has tremendously large applications that actually run very large enterprise workloads. All right, of course, not to mention Julia is open source. It's over 1,000 contributors to the language, over 10,000 packages. I'll say a little bit more about that. There we go. So the Julia community is large and growing, and we've stopped measuring downloads, when we were sort of at 45 million downloads a couple of years ago. But as you can see, this is a community that is growing heavily. One of the things that we do is a conference called JuliaCon every year, and we put all the talks on YouTube. You could look for the Julia language channel on YouTube, and and that is a very fun, vibrant channel. One of the we have a very active discussion forum called discourse.julialang.org, and then number of packages. Today we are close to 11,000 packages, open source packages in Julia. We have a very nice workflow for creating and registering packages, and for users to install them and use them. And we provide binaries, so think of packages not just being pure Julia packages, but Julia packages that can actually leverage a wealth of C, C++, and Fortran, and almost like Rust and many other languages, Python, of course, libraries written in all these other languages and plugged into Julia. So we actually also provide a complete binary serving infrastructure for 45 platforms. If you're curious about that, go check out binarybuilder.org, and that'll tell you everything about what we do there. But it's pretty phenomenal. Think about something like Anaconda, but completely open and out there. The last we had measured, we had seen downloads of Julia from over 1,500 universities that were using and teaching Julia. There are hundreds of courses that actually teach Julia today, and these are all around the world, some of the best universities. And this is this is how we at Julia Hub kind of see the whole Julia ecosystem, and this is how we structure ourselves as a business, which allows us to go and solve some really tough and interesting problems out there, but also continue our investments into the open source Julia ecosystem and grow them over the years. So Julia has, so at the bottommost layer, if you think of this as as a stack, at the bottommost layer we have Julia, which has over 1 million users, over 10,000 packages, the SciML ecosystem, the Flux ecosystem, the Pluto ecosystem, the Turing ecosystem, the Jump ecosystem. Turing is for probabilistic programming. Pluto is a notebook environment. Flux is a deep learning system. Jump is an optimization framework. And some of these packages are really, really very high quality and world class. Um, on top of these, we have the Julia Hub platform that we built as a company to make it easy for companies to bring Julia into their into their organizations. So companies such as ASML and Boeing and a variety of other pharmaceutical companies are using Julia Hub to run various Julia related workflows. Um, Okay, so that's great. But we as a company, we always started our work on Julia not just to build a programming language, but to really make an impact on the world of science and engineering. And over the years, as we spoke with our customers, we realized that we needed to build vertically integrated products across a number of different simulation domains. And we figured out that every time we spoke with our customers, and we extolled the values and virtues of Julia, like, hey, you got this amazing language, you can go out and replace all your legacy modeling and simulation tools with all this modern stuff. They would always turn around and tell us like, hey, why don't you build that product and we'll buy the product, because we are not well suited to build these symbolic numeric computing packages, but you guys are. And so that led us to first start our work on Pumas in the pharmaceutical simulation space. A couple of years ago, we started our work on Julia Sim in the physical simulation and multi-physics simulation space. We developed a circuit simulator called Cedar, which is in very early stages, and we hope to sort of build out a suite of these kinds of applications over the years, that bring sort of really this combination of physics and AI together in a way that is not just old style physics-based simulations done better, but also not just AI models, which you cannot really use for physical product development, but really sort of a blended approach where you kind of get the best of both worlds. So this is how we see sort of the world of physical AI evolving. And yes, I mean, I know everyone's kind of tired of hearing about AI, but it is also a game-changing technology of our times. And the verdict is still out there where we're going to land up. But there are a few things that we're already seeing, that can be done well with AI. And there are some things that the traditional scientific computing stacks are very good at. So when it comes to working with physics-based systems, with physical equations, with first principles based modeling, in the engineering world, we call it model-based systems engineering, for example. And those things have been very good at building first principles based physics-based systems. Where the AI technologies have been very good is at incorporating data into models in ways that were not possible before, auto-completing models, auto-completing missing physics. All of you might remember sort of studying Newton's laws at some point, and you always kind of go through all the first principles equations, but then when you're actually kind of modeling friction, you have the static friction and rolling friction, and then we kind of wave our hands and say, oh, here's a model for the static friction, and we have constants and all kinds of stuff in there, to kind of help fit the laws to the actual observations that we see in the real world. And that's the kind of stuff that AI in modeling and simulation can be really valuable for. And one of our goals is to integrate these technologies through differentiable modeling and simulation, by incorporating automatic differentiation at the language level. We've talked about this capability for years, and we are still not 100% there, but we have a variety of frameworks in Julia that have made tremendous progress in terms of exploring the different spaces of automatic differentiation that are out there. But if you really kind of step back and look at it, like why do we need this next jump in modeling and simulation? Is because the capital stock of the world is under replacement with climate change upon us. $30 trillion of capital stock will be replaced as we go and electrify every single industry, from manufacturing to transportation to food to everything else. And we're seeing tremendous advancements that we've not seen for a very long time in tough areas like space, robotics, drugs, and so on. Legacy tools are too slow, not AI ready today, and we really are entering this world of software defined hardware, right? Where software is not an afterthought in order to sort of run on some hardware, but software and hardware are actually co-designed, and the hardware design itself is rooted in a software methodology and software based process. And I'll speak a little bit about that, and hence the title of my talk, Programming Bits and Atoms in Julia. How can we bring software technologies not just to run on hardware, but to design the hardware itself? Some of the challenges in these worlds are that these are regulated industries. They're safety critical. Human life is often at stake. There's limited data available for training purposes, and there is a huge amount of investment in legacy software that is hard to move off of. And this is where we believe we have an advantage. We have a beautiful open source ecosystem with 1 million users out there across a variety of different domains. Our view is that all these products that we build for scientists and engineers are not just code only, but they're code and GUI at the same time. That there's a two-way street. Our tools have to be ready with regulatory compliance, higher levels of abstraction, modern technology, compiler technology, GPU ready, have a suite of library of verified models. And interestingly, Gen AI technologies are becoming good enough that they can actually allow a transition from legacy tools to modern tools. And they kind of level the playing field in a way that was not possible a few years ago. So, if you imagine a world where you have perfect translation, right? Just like, in the world of spoken languages, translation is getting to be pretty good. Similarly, in the world of programming languages, translation is beginning to become pretty good. And if we imagine, we don't know if this is actually going to happen, but if we imagine we reach a point where translation tools are pretty good for one-to-one translation, then the winner will be the one with the best compiler technology under the hood, right? Because you really become language agnostic at that point. It does not mean that we'll be able to write everything in C because of the explosion in the complexity of the code you have to translate, but at least within systems of the same levels of expressive power, you would expect that there will be the playing field will be sort of uniform. All right, so this is our compiler architecture for differentiable modeling and simulation. And if you look at it, like sort of at the center of this, it looks like a traditional compiler, right? You have your intermediate representations, and you have your code generation and sort of all the typical compiler passes. But what we've done is extended this entire compiler stack with passes that work with structural analysis, state selection, with working with systems of equations, typically differential algebraic equations, and sort of a lot of the tools that have been out there often do all these passes in transpilers. So they'll write a domain-specific compiler that then transpiles to C, and then you see as a regular compiler to kind of go and build your binaries or solve the problems. And what we've done is kind of build a compiler from the ground up, which adds a lot of these symbolic passes, the symbolic numeric passes on top of your traditional compiler infrastructure, allowing us to build sort of the next level of hardware, programming languages for bits and atoms, right? So for example, JuliaSim is a parser for the same underlying compiler, but which takes a description from the physical world. It takes a description of a multi-physics system. So, electrical components, magnetic components, heat exchangers, all kinds of things that you would see sort of in the physical world. chemical, chemistry equations and so on and so forth. In the world of Pumas, which is our pharmaceutical tool that we work with Pumas AI on, we take descriptions that are of clinic, of the interaction of drugs on the body, or the interactions of the body on the drug, and then we reduce it to the same underlying compiler infrastructure. Or if you think of Spice and Verilog, we are able to parse those and kind of again reduce them to the same compiler infrastructure under the hood. If you think about it, all of these worlds have been different only because historically they started out at different starting points in different communities, and they kind of evolved on their own for the last 20 or 30 years. But realistically, one can imagine that if you were starting to build this stack today, you could actually start from the ground up and factor out the common mathematics and compiler technologies under the hood. All right, so I'm now going to sort of, just go through a very quick set of topics, doing a deep dive into some of these things. So Pumas AI is actually a company that builds the Pumas tool that we work very, very closely with. So Julia Hub and Pumas have developed Pumas together. Pumas stands for Pharmaceutical Modeling and Simulation. Tons of customers around the world. There are over 1,200 pharmacometrics users out there, lots of hospitals, lots of companies. There have been over 26 regulatory submissions using Pumas, the FDA submissions, where Pumas is actually being used to make regulatory submissions. And the FDA has actually certified that Pumas and Julia are actually acceptable systems for submitting clinical trial analysis data. And it is estimated that we have together saved over $1 billion in time and money for our clients. One of the things I wanted to show very quickly is the value that, I talked about sort of Gen AI tools leveling the playing field, and I'm going to very quickly show a very brief demo of that in action.
Because I will paste a prompt that I already had prepared for you. In this case, as you can see, we have asked Pumas to generate a population of 10 subjects, which are given a single dose.
Okay, so what is happening here is that we are just, creating this, this is your typical chatbot kind of interface, and we're saying create a population of 10 subjects with a single dose of 100 milligrams at time 0, include weight and covariates, which should come from normal distribution with the mean 90 kilos and standard deviation of 10. Conditions should come from a, Bernoulli distribution with probability of success 0.7, right? And traditionally, you would have, the users had a Fortran library where they would write all of this stuff in some kind of a DSL and then go and execute it. But of course, the Fortran library is increasingly falling out of, maintenance and is increasingly harder to work with. And so now there's a new tool called Pumas that is doing all of this. So you go ahead, you hit enter, and you get this.
So we got some explanations, but more importantly, the Julia and Pumas code that we requested, which I'm now going to copy over to my editor. So now that we have the code, let's just go ahead and run it. And as you can see, we get the 10 subject population with the covariates that we requested, because I will paste a prompt that I already had prepared for you. In this case, as you can see, we have asked Pumas to generate a population of 10 subjects, which are given a single dose and have some covariates that come from very specific distributions.
Sorry,
And
I think
right
I
as
just ended up
editor,
going back. And
how it came up with that answer. But even more interesting than that is the last section of the answer, which is labeled as sources. Let's just click on the first link to show you what we mean.
So, okay, so you get the general idea here that, this is actually, took some clinical trial data, generated the code, ran the simulation, came up with an explanation. So really very nice, way to integrate, the powerful Gen AI tools within a very deeply domain-specific regulatory scientific workflow, where, we're not going and saying that, hey, the AI is going to replace the scientist, but actually this is tremendously accelerating the adoption of a new system and reducing the barrier to entry for scientists to start doing this kind of modeling and simulation. Okay, so that was the pharmaceutical world, and that's something that we work on with our partners at Pumas AI. Feel free to reach out to them on their website or to me, and I'm happy to put you in touch with them if you're interested in those kinds of tools and technologies. And now I'm going to focus on multiphysics simulations with Julia Sim. This is a tool that we are developing at Julia Hub, and it encompasses, a very broad set of capabilities from model development to model deployment, right? So we want to be able to develop models from first principles, first principles physics. We want to use AI capabilities to integrate data into models, to do model auto-completion, to calibrate the models, to discover the missing physics, do all the analysis, and then hit a button, deploy the model, and a control system onto an embedded server or onto an embedded device. And all the while we do this, we are building a suite of very high quality, deeply, high quality, high fidelity physical libraries. So we have a batteries library, we have an HVAC library, and we are building a broad list of components that users can literally just drag and drop. And if you think, these libraries are extremely hard to extremely hard to build. For people who come from the software world, it's often very hard to fathom the level of complexity that these libraries have. They often take over a year or two each to develop, using some of the best experts in the field who have to straddle computer science and physics and some engineering discipline. It's just an extremely difficult and time-consuming process. And the libraries then have to be validated with test data from real experiments or the lab, because if they're not accurate enough with real world phenomena, then they cannot be used. So I'm going to kind of move a little bit forward, and I might end up skipping some of these slides. So when it comes to multiphysics simulation, in the engineering world, the modeling process follows this V cycle, right? So you start out at the very high level with a system specification, and then you increasingly decompose your system into systems, subsystems, assembly, components, and then all the way down to actual manufacturing of the individual parts, writing all the embedded software that'll run on it, and then you kind of go about testing each of those individual components and then recursively integrating them back up the stack until you have kind of integrated them into the full system. And then once you've done that, you have sort of the asset deployment in the field and maintenance and logistics, right? So prognostics, sorry. So think of your jet engine, being a component in a plane. The jet engine itself would have, a V design. Your plane would itself have a V design, like every component in the plane, right? Your, everything from the flight control system to the environmental control system, to the operation of the lavatory in the plane, right? Everything would have sort of this entire, V cycle that would be done. And everything has to be designed and then tested out and then deployed. And once you deploy it, you get real world data from the field that you can then deploy it, have digital twins, improve the operation, improve the optimization. You have wear and tear. You have to model, you have to use the physical models that you built at the design stage to then model the wear and tear and then kind of move forward. And typically, what's relevant for us as a business right now is that we operate above this dotted red line. So, everything below the dotted red line is geometry based, and you end up using partial differential equations that incorporate geometry, but everything above the red line is ordinary differential equations and differential algebraic equations that are sort of using the compiler stack that I just described in a couple of slides earlier. That does not mean that our stack cannot generalize to PDEs. It will. It's just that you got to start somewhere, and we started out in this higher space, in this sort of in the sleeves of the V rather than at the bottom of the V. And our goal really is to sort of take the software, the software approach, right? The software-driven approach to hardware. So I take the software development process and bring a software-driven approach to hardware, where you sort of, kind of follow the typical, test-driven software development, work fast, release often, hopefully don't break things, but kind of, rapidly iterate inside, using sort of modern software methodology, modern software development methodologies, and incorporate them in this V cycle for engineering design. These are all very stylized views of, if you actually go down in the real world and actually do all this, it may not physically actually exactly map to all of this, but it does a pretty good job. So one of the things as we speak with scientists and engineers is that they love the idea of software-driven methodologies. However, they don't want to see themselves as writing software all the time. And there are times when just defining the GUI, defining your models through a GUI is far more effective than writing it as code. And there are times when writing code, for example, to interface with the real world, with sockets, with data streams, with messaging systems, is simpler to write as code rather than sort of through visual programming. And so what we built with Julia Sim is a visual programming system that incorporates both a visual style of programming to build your models, but then also with a click of a button, dropping down into VS Code and then hand editing the model should you need to, or writing other pieces where the model interacts or the control system interacts with the real world. And so these are some of the systems that are commonly used in these two worlds, and we expect Julia Sim to sort of straddle both. One of our key innovations in all of this is the scientific machine learning ecosystem. So which brings together data and models, or data-based analysis tools and model-based analysis tools in an amazing open source ecosystem that are packaged underneath our products. And some more examples of what AI does. I'm kind of beginning to run out of time here, so this is a slide on how surrogates, how we use physical surrogates to speed up simulation. So for example, here's a simulation of an electric vehicle, of a battery system, where the state of charge is being modeled using on the left with on the left here, this little, there's a car that's driving on this map, and it's taking this is the left side is the physics-based simulation, and the right-hand side is a surrogate that has been trained on the battery simulations, but now is running in real time because it is simply running the surrogate AI model rather than the actual complete physics-based model. The physics have been compressed, into this surrogate, and you can see that we are driving here from our office in Cambridge to MIT, and the car has barely just left. I'm just gonna, the car has barely just left this building on the left, left the parking lot, whereas the car on the other side, which is a surrogate, actually has already reached MIT. All right, so I spoke about why Julia Sim. What I'd like to do is talk about a few of the customer use cases. These are some of the pictures and schematics of the models and what the system looks like, and and what the diagramming system, the visual programming looks like. But I don't have time to cover a lot of that. I will say that if you are sort of in a company that is doing that is using technologies of this nature, we have a consulting services team that will help you make all this happen. But let me share a few case studies with you. So at NASA, they designed this this launch. The NASA launch folks designed a Julia Sim-based model to replace Simulink. This is from their talk, which shows this the spacecraft separation dynamics, which in this case turned out to be several thousands of times faster than Simulink. And you can kind of see this Monte Carlo simulation being visualized out here.
Hey, Viral, sorry to interrupt. Just a quick time check. We are 30 minutes in. Yeah.
Thank you.
Go ahead.
So the U.S. Air Force Research Laboratory, built a drone. That's not a picture of the drone. Actually, it's a different picture. The actual relevant text is here. That they built a drone that used a control system written in Julia for doing automatic path planning in flight using nonlinear control algorithms. Traditionally, control algorithms that run on devices are very simple. They're often linear PID systems. And one of the big transitions that is going to come up is because of the amount of silicon that is being added onto physical hardware today. I mean, you're having sort of cell phone level compute, or even more, that is available on physical hardware depending on the power envelope and the operating envelope of these devices. And one of the things that's possible as a result is to go beyond traditional compute bound controls methods and go towards model based control, nonlinear control, incorporating sort of all these tools and capabilities. We were able to sort of, again, build, I showed a surrogate of a battery. Here's a surrogate of a jet engine that has been built again, runs with 0.1%, runs with 99.9% accuracy, but runs, in microseconds as opposed to minutes. Here's a model of a scientific machine learning model that we built for Williams Racing, for the Formula One team. And there are two models here. There's the Julia-based model, and there was a traditional old Python model that they were using that was purely data-based. The left on here is the Julia model that is scientific machine learning based. And as you can see, not thinking too much about what's happening under the hood here, so sort of the underlying purple and the yellow things are actually sort of what the model is predicting, and the actual car here is what's happening in reality. The sensor is trying to predict, or rather the software is trying to predict it's a software sensor, so it's trying to predict the speed of the car and the angle of the car on the track. And as you can see that if you incorporate first principles physics-based systems along with data-driven techniques, you can actually come out much better than the car on the right here, which is, it's kind of getting there, but it's a bit janky. It's a bit, and there are times at which it's completely the opposite as well. We built a ground penetrating radar stack with Julia Sim in the signal processing domain, guidance, navigation, and control systems, working with aerospace companies. ASML, one of the world's most complex companies, uses Julia in a very large way to for the development of the software that runs on their TwinScan machines. And they gave a keynote at JuliaCon, which is available online. If you just Google JuliaCon and ASML, you'll hit it. And that's really sort of fascinating talk of why a company like ASML is using Julia. Another company, Instron, which builds these massive catapults that build car crash testing systems, uses Julia to accelerate the development of their models, but also sort of the runtime of their models. Julia Sim is deployed for the optimization of wind energy, wind farms, and so on, right? So tons of very interesting applications in all these different industries. All of this runs on Julia Hub. Oh, I think I messed up the placement of this slide here. Another example from a water utility. People think of like, oh, what's the big deal in water, right? But think of sewage treatment, think of water supply, think of all the pressures and pumps and pipes that have to be sort of correctly modeled and installed in order to kind of make your things deliver a reliable utility, right? Have a reliably running utility, and that's another one of these Julia Sim use cases. All of this runs on Julia Hub, which is our cloud platform that runs Julia, along with we provide a VS Code IDE, batch CPU, GPU, the ability to run third-party software in Windows and Linux, notebooks using Pluto, full integration with Git for version control, files and data sets that are versioned, and the ability to develop private packages in addition to all the packages you build. And all of this can be deployed on the cloud or on-prem. So really, this is what we aspire to as a company, is provide a modern cloud-based modeling and simulation, a suite of modern cloud-based modeling and simulation products for industries, and really sort of raise the level of abstraction for engineers and scientists worldwide, build an incredibly successful business while we are at it, so that we can keep investing in more and more domains as we go along. And if you're interested in being a customer, or if you're interested in working for the company, write to us, and we'll be in touch. Thank you.
Hey, thanks, Vera, for the awesome talk. I think if there are any questions, I can see one question from Sachi. I'll just quickly go through it. Hi, Viral. Crisp and informative talk. I had a question along the lines of AI and domain-specific applications. In my experience, these Gen AI tools work well when they have a lot of data to work with in the domain. For example, the Pumas AI works well for pharmaceutical-based use cases, but would not work as well elsewhere. Even the V-shaped design you showed, if I asked a model to work with Julia at the PDE level, I think it would struggle. What do you think can be done with the problem, especially in relation to maybe learning from languages with the same expressive power?
Um, it's a very good question. So, obviously, first of all, there are all kinds of people out there who are, selling technologies like physics-informed neural networks, who are sort of pushing for things like world foundation models for physics. And, of course, NVIDIA gave a tremendous demonstration on the robots simulation and the physical AI and all of that. However, it's important to be clear about what we can and cannot do, right? So at least as of today, these technologies cannot go and solve your PDE for you, right? You cannot just take every PDE in the world and solve it for every possible geometry and then have it spit out design relevant or design level solutions or rather spit out physically accurate results of simulations that can be used for design purposes, right? You would not go ahead and design the wing of your airplane using the solution of a PD that a potential AI system might have given you. At the very least, if such a thing existed, you would have to then go back and run it through, tried and tested CFD simulators, right, that are out there. However, there is a huge body of code and documentation around design processes, around requirements, around certification, around validation that are inside of companies, and AI systems can go and learn from them, making it easier for engineers who have to develop this stuff. A lot of times we do not realize that the work of building or developing hardware is actually not sexy, right? You're not actually sitting out there firing the jet engine, and seeing that big plume come out at the big fireball come out of the back. A lot of times you're sitting writing requirements, you're writing test cases, you're running these things over and over again, you're making small changes, you're simulating these things, and you have to write a lot of documentation for safety reasons, but also for design reasons. These are large teams, there are communication challenges, and there is a great possibility of just using Gen AI tools today to kind of simplify these workflows. And it's kind of exactly the same thing that you see in software development, right? That you don't get to do the fun algorithm development parts all the time. You actually spend a lot of time doing other stuff in order to write your software. And the same is true of hardware. And I think some of these tools are going to actually make it really nice for us.
I hope that answers Sachi's question. Yeah, seems like it. There is another question from Sanjay. Thanks for a peek into the future. Question I have is whether there is a specific aspect of Julia that makes these possible, or is it the power of the underlying compiler that you mentioned that's responsible?
Yes, so that's a very good question, that why Julia, right? Like, could I have done this in C, or could I have done this in Rust, or could I have done this in Python, right? Or could I have done this in R? So the R and Python answer is easy. I don't think it would have been easy to do that because they're fundamentally interpreted languages that leave a lot of performance on the table. And so you would have just kind of boiled down to rewriting everything in C++ under the hood. And the velocity for developing systems like the kinds that we have would be extremely, extremely slow. And this is also why, languages like Mojo that have built these things for machine learning purposes, again, right, are not built on Python, but they exhibit a Python front end while implementing a brand new compiler under the hood. C++ would obviously be a very low level language to work with. And it would not sort of be a good fit for the end community that we're working with. So we really need to sort of straddle this. Like, we need to have sort of the best computer science under the hood, but we also need a user interface, a programming user interface that works for people who are domain specialists who are not programmers otherwise. And hence, Julia is one such system. Maybe there could be other such systems, and I'm sure more will come up. But as the reason why we set up Julia was because we wanted these things that we knew what we wanted to build out these products. And there are some things that Julia gives you that are very nice. So multiple dispatch solves the expression problem, for example, and allows you to sort of build these capabilities out without kind of shoehorning you into an object-oriented, purely object-oriented or purely functional paradigm. But multiple dispatch actually maps very well to the mathematics that we're talking about. And it goes up all the way from just doing a simple addition to solving the model of an entire airplane. And so multiple dispatch has been tremendous a gain in productivity for us. Of course, it brings other challenges like specialization, code generation, compiler performance. And if you've been following the Julia development, We have sort of made tremendous progress on all these topics. It used to take us 30 seconds to make a plot because we were compiling the plotting system. Today, you get a plot within half a second. With Julia 1.12, we are going to have Julia C, or, Julia C is kind of like GCC, right? Like the Julia compiler that would allow you to generate executables and DLLs, or shared libraries, .sos, from your Julia programs that kind of look like C generated static libraries and executables, so that it can be incorporated into other workflows, other systems, and so on. So really sort of long-winded answer, but it's all about productivity and having all the things and kind of building these things rapidly.
There's one more from Amok. I have heard a lot about multiple dispatch mechanism in Julia. I was wondering, how is that made performant when the language was being built up from the ground up?
So this is a very good question around multiple dispatch, right? So the way you make multiple dispatch fast is by specialization, right? Because multiple dispatch essentially, it's polymorphism, right? So for every combination of inputs that I can give to a function, every possible tuple of types that I can give to a function, what we end up doing is specializing the code generation for that function, right? So the code that is generated for adding two integers is different than the code that is generated for adding an integer and a floating point value, right? At the very simplest level. And the code that is generated for adding two dense matrices is very different from the code that is generated for adding a sparse matrix to a dense matrix, and so on and so forth. And it is this specialization that makes the language performant by design. So it's not an optimization. The language is fast because of its underlying inherent design, which combines multiple dispatch with specialization. And if you look at sort of our paper on Julia that we published in 2017, it's on our website, it's on Google Scholar. We actually kind of delve into a lot of these mechanisms in great detail.
Are there any further
Comment about
questions?
cell phone level compute being a mind bender. It's kind of crazy, but it's true, right? Like, you have Raspberry Pis and more in all your embedded devices. And think of the car, right? In automobiles, for example, 6% of the bill of materials of a car used to go to silicon, 10 years ago. Today, I've heard that number is close to 16%. In another 10 years, that number is expected to go to 30%, right? So think about all the power budget that you will have, a compute power budget, not just the battery power, but the compute power budget that you will need for autonomous driving, powering all those sensors, processing all the video streams, and then the car having to make all these decisions, as you go about designing and driving, and everything is becoming autonomous, right? Not just cars. So, everyone's seen all the demos around, so I don't need to sort of talk about all the things that are happening in the world around us, but it's a tremendously exciting time. The other fun phrase that I've heard is from General Electric, right? That they build these locomotives and they call them as rolling, they call them rolling data centers, which is kind of like a fun term as well.
If anyone from the audience wants to talk with Viral directly as an interact, you can raise your hands if interested.
Hey, Viral, thank you for that short answer. I think I'm more interested in uh, reading or at least watching, because there is a video in the chat about what makes Julia fast. It's a topic close to my heart. One question, just wanted to ask you was like, what motivated? I mean, you're one of the creators, so that's why the question. You to create a new language, not the design decisions, but what were the experiences perhaps that led to think that, perhaps a new language would make more sense. Uh, these things are not there, or I do not like the experience that I'm having. Generally, there is some problem that a creator faces in their life while working on something where they feel the need for a new tool to be there. So were there similar scenarios with, or what were you using before Julia for the same?
It's a very, very good question. So actually, so I got my PhD doing high performance computing at UC Santa Barbara, which has a very good computational sciences and engineering program. And It's kind of like this joint program where you don't just do computer science, but you also study classes in engineering and math. And then your PhD topic usually is something that is related to computational sciences or engineering. And my talk was focused on, as my thesis was focused on doing large scale parallel graph algorithms, but in a way that that was a high productivity system. And so the way I did it was, using what evolved later on into the graph BLAS system, or sort of, a BLAS for graph algorithms. So I used sparse matrix capabilities to build large graph algorithms, and then scaled it up using distributed sparse matrices. The language that I used for implementing all of this was a parallel dialect of MATLAB that was developed at MIT. It was called StarP. But we were constantly fighting sort of the challenges of MATLAB itself, right? Because it's a closed source language. It's not as fast as you need it to be. It's maybe it's sometimes faster than Python, but it's usually pretty slow. Like often, people write MATLAB codes and find that just a straight translation to Julia will give you 100x faster system. It did not run natively on GPUs. So it was really sort of, like while my PhD dissertation proved out the possibility of using a distributed sparse matrix infrastructure embedded in a language like StarP to do large graph algorithms, it really sort of left a lot on the table. And later on, I was discussing this idea with one of my fellow students back then, Stefan Karpinski, and a colleague at work, Jeff Bizanson, and Alan Edelman, who was on one of my thesis committee members out of MIT. And the four of us just started talking like, hey, this has been really painful. All of us had similar shared experiences, and that led to the creation of Julia. So in some sense, it was 10 years in the making at that point already for me. Collectively, for all of us, it was 40 years of thought had gone into this point at which we were ready to start Julia. But then really sort of, the moment we started talking about it, it's crazy. I still have those emails. The time from, the first email discussing the possibility of a new language to having a parser for Julia was literally less than a week. And that parser and language spec that we had is still over 95% the same, like 15 years later today. So it was really sort of a fun time. And of course, when it's great to kind of be there witnessing the birth of something like this. You have no idea where things are going to go. We just started this as a hobby to scratch our itch, but it turns out it scratches many itches for a lot of people. And I've given many other talks that talk about sort of how we sort of you built out the Julia community over the years. And there are like lots of talks at JuliaCon, lots of talks from Chris Rackauckas on scientific machine learning. There are a lot of talks on Julia Sim, a lot of webinars on the Julia Hub website that dive into many, many different technical aspects of all of this. But it all started out with that one email of frustration.
Thank you, Viral, for a detailed answer. Just a follow-up, if Yogesh will allow me. So the follow-up question was that, do you see Julia being adopted outside of like being a more general purpose language, where and what does it bring to the table in say when it comes to classical say web development or microservices backend development, right? Those kind of spheres where you have languages like Rust that are coming up, and there is Go, and then there are other languages. I guess these will be the close ones that play kind of around in the performance
Yeah, so when you build a programming language, you can't be everything, right? So programming languages are some of the most powerful tools humanity has created, right? Think of Turing completeness, right? Like how many products do you know in the world that have that level of expressive power and generality? Programming languages are one of those very few things, but with great power comes great complexity. So when you build programming languages, you end up typically picking a set of features and making trade-offs that make them good for certain things and maybe not so good for other things. Even though in theory you can do, anything that you can do in one Turing complete system, you could do with other Turing complete systems as well. So, Go was designed to solve problems at Google, for building large networks, services, web services, all that stuff. Rust was designed for building, systems, applications, right? Browsers, operating systems, and so on and so forth. And their underlying sort of design trade-offs are made in those directions. Now, of course, all these languages are constantly borrowing ideas and stealing from one another, right? Like how should we do garbage collection today, or how should we do code generation? Or a lot of them use LLVM under the hood. I mean, Go does not, but Rust and Julia do, for example, right? How do we do cross compilation, and so on and so forth? So the answer is that Julia is well suited for all of these. There is a beautiful framework called Genie for web development in Julia. There are a number of web packages. There are a number of networking packages. There is a whole general I/O asynchronous programming system in Julia. But the ecosystem of people that work on Go and Rust when it comes to systems and networking is significantly higher. So the kinds of libraries, the kind of development that you see in those ecosystems is much better in those languages than it is in Julia. I, for example, would imagine that there might be a world where so like I said, one of the things is Julia 1.12 is coming out with the Julia C capability, which will allow you to build static libraries and binaries out of your Julia program. So that could be compiled to WASM and deployed onto a website. That could be compiled into a small embedded program that runs on a tiny Raspberry Pi Zero kind of device, or it could run on an HPC, for example, right? So I think that this ability to do Julia C based generation of binaries is going to be tremendous in terms of expanding the use cases of Julia. But really, I think the question to ask is that the core ideas in Julia, right, around multiple dispatch and generic programming, where are they the most valuable? And where do they kind of give you something that the existing systems do not give you? And I'm not a person who has thought deeply about network programming. I mean, yes, I've written tons of it, but can I imagine an experience for people who build, network systems that would be better than Go using the ideas that Julia provides? And if so, then, you have all the underpinnings, you have everything open source, and you can go about, defining things. And there are many, many academic systems that explore these kinds of spaces if you kind of look around on the Julia discourse or on GitHub. But at the end of the day, like, my personal goal when I started was sciences, right? And that's what we are, science and engineering. And one of the things we do, like all the products I spoke about, Julia Sim or Pumas or even Cedar, it's interesting to note that they actually reduce the expressive power, right? It's by reducing the expressive power of the DSL, we are able to provide higher levels of abstraction and experiences to those engineers and scientists. And so it's a very interesting sort of balance. So as you go about building the stack of tools, not just Julia itself, but sort of all the other things that I've spoke about as well.
We have one more question from Sanjay. I'll just read through it. I have one more question. I have to imagine at least some of the use cases you described has to run distributed across many machines. Does Julia interface with the Beam stack or anything similar to it?
So Julia has an inbuilt distributed computing library called, a standard library called distributed.jl, which pretty much just uses communication, socket-based communication to exchange Julia data structures over the network. Actually, it is, if you are a systems programmer or distributed computing programmer, it would be very good to kind of look at distributed.jl. There is a next version of it that is being built called distributed.next.jl. There's a small community around it that kind of keeps it going. And it could actually use a tremendous amount of development going forward from where it is. But it's actually pretty usable for doing distributed computing. A lot of the scientific users in Julia actually use MPI, which is an old message passing interface designed in the C/Fortran era. And MPI works very well with Julia as well. And we provide sort of access to all the national lab distributed computing libraries, through the Julia binary builder mechanism. But I don't know what Beam is. However, it shouldn't be that hard to build an interface to the Beam stack. If the Beam stack has a C API, Julia can just literally call any C API without even needing a compiler. You can just C call it in Julia. But you do have to think through garbage collection and ages of objects and closures. Like you have to think about what that means at a language level at the end of the day.
All right, one more question from Sachi. She has a follow-up question on restricting the expressive power. What exactly does that mean? Why would that be required to increase the power of abstraction for users?
Yeah, so think about it in this way, right? So compilers can do better when they're given a well-defined constrained environment, right? So if you write your C program with pointers doing all kinds of crazy stuff all over the memory, that program, would have very little structure in it, right? So the more structure you can put into your program, the more bounds you can put on the program, the more the compiler can analyze what it's trying to do. What the user is trying to achieve, and can apply a level of optimization that it may not have been otherwise able to do if the program was strictly general, right? And so as you curtail the expressive power of languages, you can actually build DSL compilers that are able to do a lot more, because they can enable new optimizations which would not have been possible to apply when the power was very high, or when the system was too general, because compilers have to always operate in the worst case scenario, right? They have to be correct for sort of any accurate, they have to be correct for any description of a program given in the allowed syntax with that level of expressive power. And they cannot, unless they can prove things computationally at compile time, properties about the program, they cannot sort of apply all the optimizations that you might want to apply. So there's a series of blog posts even within Julia around the nature of compiler optimizations that we can do in automatic manner. But it turns out that if you're solving problems for engineers in physics and drug development and so on, that's a very constrained environment, right? You're not writing a general purpose network program. You're not writing something that can run on a small device that can do just about anything. You're solving a very, very highly specific program, a kind of computation, and the decrease in expressive power allows us to do a lot more optimization. And a good example is, like, for example, if your DSL does not have if statements, then you might have straight line IR in the program, and compiling and optimizing that is far easier than optimizing programs that have conditional statements in them, or unbounded loops, for example.
Cool. I think thanks a lot, Viral. We should start wrapping up and letting you also enjoy your, I guess it's Sunday morning for you, Saturday morning, sorry.
Thank you. Thank you, Naresh, for having me, and hope this was a fun session for everyone. Thank you. Appreciated the questions.